Okay, let's see. Okay, we're recording. How we doing, everybody? Doing good? We're already at the end of the semester, right? Yeah, it's a tiring one, too. It's okay. You guys are doing great. Anyways, how's the lecture going?
Good.
Pretty good?
Pretty good, but he does like advanced things.
Advanced things? What do you mean?
Yeah, like he's mixing stuff that would normally be introduced in E361 into like
But
E361
then
now.
he says don't do that.
Don't do that.
Wait, do what?
Don't do
The
that.
advanced shortcuts.
Yeah.
What kind of shortcuts?
Which kind besides like the heavy side was it heavy side cover?
He says don't play with the Z, keep it at Z -1 instead. And then he's like, he does other shortcuts where it's like, but don't do that. Do it more rudimentary and more basic.
I think I know what he's making you do, and personally, I would actually be not. I'll be like, yeah, you know what? Do it two ways. You're gonna do it the conventional way, and you're gonna do it the cooler way. Full points, 20 points each question, 5 questions each, or I don't know, something. So do the same problem, but with Laplace. Do the same problem, sample it, do it in Z. So I'd probably get, and then you have the conventional way, you have the Z transform and the S transform. Is that cool? That's what I would do, personally, not gonna lie. Because have you noticed, okay, we stopped doing convolution, right?
Yes.
Painful, right? He's gonna make you do that on the exam.
What?
Or the final. I don't know. I really don't know. So yeah, you're gonna have to do it again because he wants to make sure you know that as a signals and systems person. Okay. Plus it's good for your MATLAB as well because you have those. What do you call it? What's the word? It's the long word. Linear constant coefficient difference equations, right? Difference equations. So there's a difference, n-1, n-2, stuff like that. But then you notice, hey, I can turn this into z's, and you can go into the z transform, and things become a lot easier. And personally, it should, because you got who do we thank for that one? Who's in charge of the z transform? I don't know. Laplace was made by the guy Laplace. Fourier was Fourier. Who made Euler's equation? Euler. See, who made Ohm's law? Ohm? I don't know. What about Ampere's? Ampere? Yeah. What about Maxwell's equation? You see, there's a name to everything. It's pretty cool, right?
Clark Maxwell?
Yeah. You see, there's a name. But anyways, what about Z transform? I don't know. You tell me.
Oh, can I ask one before we start?
What's up? Well,
This.
oh no, you're gonna have to do that tomorrow. Okay?
Tomorrow?
Yeah, tomorrow. Okay. Anyways, let's see. Where's your class? Does he keep it? Where does he keep stuff?
The class website, so just go to
Oh, okay. So Morris. Boom. Happy face. Boom. Click. Can't press F5 just in case it shuts off the power. Or there you go. That's your grader. She's out for the day. Let me see. Let's see. Oh, he finally published the other, or no. Yeah, the other YouTube. Great. Here's your comps 6 right there. This is today, right? Right? And then this is next week. We're going to have a review. Everyone see that? And then what day are these? Let me see. 414, 416. So what day would this be? 415, right? Next week. We're going to go over the exam or problems from the exam or a practice exam. I don't know. Wink, wink. Please come to discussion so we can go over your questions, all right? Anyways. And then he should have your state space equations done, okay? You haven't gone over state space analysis, but this should be a pretty cool assignment. So basically, is there another way to do the MATLAB assignment? Yes, there is. So much more easier because Laplace Z is just, things work. And that's how a lot of MATLAB is run. They use state space equations. But I'm not going to talk about that. We're going to talk about, click here, assignment, okay? I want to go home. Everyone started it, right?
Yes.
Good. Not that bad, right? Actually, let me ask this other question. How's the last assignment?
I thought it was really bad. Was it? It was supposed to be pretty easy, right?
Let's look at it. Okay, we're gonna walk through this together because I don't want no one complaining.
I used your reference code and then just like kind of iterated it.
Derive the system transfer function. Everyone can do this in this class, correct? Everyone can do this in the exam, right?
Yes.
Good. Calculate the transfer function. Sweeping S, right? We did that, right? Easy, and you guys got to see those cool plots. Not that bad. The frequency response, right? For those who took my 320 frequency response, you guys got to see some Bode plots or some slopes. If you don't put 20 log base 10, you're going to see the weird linear curves, which is okay. Actually, maybe I should have kept that. LT Spice. You guys like LT Spice?
Yes, actually.
This is an RC filter, right? How do I calculate the knee frequency? 1 over 2 pi RC, right? So if I were to find it, let me just click on this, right? Actually, let me make this red. Right? Pretty cool, right? Where would that frequency be? 3 dB, right? Let me just see, where does it go 3 dB? Actually, here, you see these numbers right here? 3 dB right there, right? Minus 3 dB. I usually go with this guy right here because it's easier to find the 45 degree than it is the 3 dB. Let me show you what I mean. So if I look at this number right here, let's see when it turns to 45. All right, close enough. Actually, let me just super zoom, okay? Then where's my mouse or my cursor? Right here. 45. Right, close enough. Is that cool? Does everyone see that? And then I can do zoom to fit, and then I can do this, the following like this, and then I can publish this in the lab, right? Everyone understand what a frequency response is supposed to look like? And this is an analog frequency response, okay? Can I show you a digital one? Not an LT Spice, but the point is you can do Laplace transforms with not cadence, LT Spice. You can, if you're taking my 420 lab, you can do the same thing in cadence, and you can build a chip. Is that cool? Anyways,
Do you have a tutorial for how to build something in Cadence?
yeah, just take my lab.
I didn't take the lab.
That's where I teach everything, okay? Anyways, easy stuff, right? Not too bad. You know what? I'm gonna run this again. It's so fun. I enjoy signals and systems. It's a cool topic. Let me see. This is the S, okay. I'm gonna save as, okay. I'm gonna save this again, okay. I'm gonna call, what lecture is this lecture? I'm gonna say lecture 9, whatever. Okay. So, remember, everyone got Computer Assignment 5 good, right? Not that hard, right? Let me just do something funny. Hear me out. Should I don't know if I want to waste time on this, but you guys know what the transfer function of an RC circuit is? I don't hear any good answers. What day is it today? April 8th, 2026, page 1. Okay. Right? In terms of S, what's the transfer function? Or Vn, right? What's the transfer function? Not hard? How do I make this easier? Everyone understand what's going on? Where's the pole?
At S. What do I at negative S?
Right? So when S is equal to this, right? Then this whole thing turns into -1. Boom, you had a pole. Right? Does that make sense? What are the numerator terms in terms? Okay, I'm gonna build something. Okay, h of s. Okay, in terms of MATLAB. I want everyone to build these systems. Okay, this is something I want you guys taking home. Okay, the numerator, right? Is there any s's there? No, right? So I'm gonna do this. I'm gonna do. Okay, I'm just gonna write this for completeness. Okay, just in case you want to build a second order system for your exam. S2, S1, S0, okay? I'm going to create the numerator, denominator. You're going to do this for your computer assignment 6, by the way, okay? Well, not this, but it should be a hint. Do I have an S squared term on the numerator? No. What about an S? No. So 0, 0, 1, right? Make sense? I don't have a square here, right? But I have this S right here, right? So it's going to be RC, right? And then this one is going to be a 1. You guys see this? Let me just do this, okay? Because I want to make sure everyone understands what's going on. I'm gonna circle this right there, right? I'm gonna circle this right there, right? What am I gonna do in MATLAB? A's and B's, or is it B's and A's? MATLAB, A's, okay? 1, or no, 0, 1, right? And then what's my B? It's going to be, oh, bless you, RC, R times C. Actually, anyone bothered if I do this? Where tau is equal to R times C, right? Is that making sense with everybody? Let's see, Z plane. Why do I have that there? Let me see. Is that good with everybody? Let me see. I want to show you something cool before I go crazy. Here's my numerator. Here's that. Let me just copy this. Mesh grid. Poly. Okay, this is right here. Okay. Boom. Oh wait, no, right here. Okay. Everyone see my RC circuit right here? Right? Should I make R equal to 10K? Oh wait, 10E3. And C is equal to 10E minus 9. Everyone understand that notation, engineering notation? Boom, RC circuit's built, right? We're building our S-plane, right? Same thing for the Z-plane. I'm giving you guys super hints, okay? Okay, and then zeros, and then calculate, and then what else did I do? Let me see, because I'm copying and pasting things because I want to go home. Boom, copy paste. Boom. Okay, and let's run this. Control Enter. Something barked at me. Oh, because this should be my numerator. My numerator is A, and then my denominator is B. There we go. What is going on? Let's see. What did it bark at? Oh, sigma. What's sigma? Minus 10. No. Let's see. How do I want to do this? E. Where's our pole? Let me see. Our pole was at about, what did I say for our pole? I don't remember. This is about 1K. So multiply that. Okay, that's frequency. S equals 2 pi F. So F divide this. Okay, so it should be right here. So it's going to be around 100. So I'm going to do the following, okay? Someone's going like, what the heck is David doing? 10E3, okay? And then omega is equal to 10E3, okay? I'm creating my frequencies, okay? Boom, 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 poly. Get rid of this, boom. And let's run this. What did it bark at? Imaginary. Oh, H, okay, SM, okay, sigma, omega, okay, Give me a second, y'all. Z? Am I using Z here? Polyval AS SS figure S real H. The function used to get real values. Okay. Let me CLC. Let's run this again. Let me see for realsies. Okay. The surface Z must contain more than one row or column. Where is this one? Line 63, but not there. It's complaining right here. S real. S imaginary. Mesh grid. Oh, you know what? I haven't slept. You're going to do this for your assignment, by the way. Sigma, Omega. I forgot to declare rows. Don't do what I did. So what do you think I'm going to do? Just copy paste it, okay? Don't worry, this is all for your assignment, computer assignment 6. I'm just trying to show you an example, okay? Boom, 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 boom. This is my frequency. Sigma 10E3, 10E3. Actually, that's a lot of points. I'm going to do 10, okay? 100. I think that's a lot. Okay, E3, E3. Okay, we're building. Let's go. Come on. Oh, yeah, let's go. Oh, dang, this thing is heavy. All right, real axis right here, right? Right, going from left to right. Imaginary axis going up and down, right? Is this a stable system?
Yes.
Why?
Right-sided?
Yeah, it's a right-sided function because the pole is on this side of the axis, right? Is that cool? Everyone see what's going on? And then what if I cut it right here in half right here? I get a frequency response? Better yet, let me show you the frequency response. Sigma, let's get rid of sigma. 1. Let's look at omega, okay? Now look at that. Is that looking like an RC filter? Not yet. Let me show you. Is that an RC filter? And you can't really see it because you know why? Let me show you something cool. If I were to just get rid of sigma, oh, it didn't like that one. Okay. Let me just do 1. There we go. Ooh, that's milk. Yeah, that's good. Arr, I love that. Is that an RC filter? Let me see. Did I do it correctly? 20 log 10 absolute H. Let me multiply this by 10. Is that okay? No, it's linear. Why is it linear, y'all? H. Oh, you know why? This needs to be converted to semi-log x. Semi-log x. What do you call it? This might be good for you, but let me show you what I mean. Bless you. Omega is equal to linear space. No. What's log space? There we go. I don't know how to use this function. What do I do? There we go. Logarithmically spaced vector. Let me see. From this point. Oh, okay. So I want to go from DC to 100E3. I don't know if this is gonna work. Oh, yeah, I don't think it worked. E3. Oh wait, no, oops. There we go. Hey, is that a Bodhi plot? Is that better? Let me do 4, 6. There we go. Oh, but it's not multiplying. Do you see the problem? This is not doing what I want it to do. It's not scaling. Everyone see my problem? It's a problem with mesh C, and I don't like that. Anyways, let me show you an example because I'm tired. Any questions?
Wait, you see you're tired, right? Can we go home?
No. Because then how am I going to help you with your computer assignment 6?
Yeah, okay, right.
Oh yeah, we can go home. Yeah, you guys can go home and won't do your answers. Okay, cool. Now you can do LT Spice and MATLAB and prove with everything I showed you. All right. Anyways, let's get rid of all this. Actually, except for this, because frequency response is important. No more kicking boxes. Okay. Frequency response. Remember from your assignment. Okay, frequency response. Right? Omega, right? W, something like that. Because I'm trying to think about why everyone was like, okay, I'll spill the beans. Dr. Moore is like, yeah, go over the assignment because maybe they might complain. Was this assignment hard? No? So basically this is all extra information, right? Which is good, right? And point is, I don't want to waste your guys' time, okay? So yes, what's up?
I mean, I was looking at your structure, and you structure some of the coding assignments into making it break down the same way you would think in terms of like the equations I'm testing. I think it's like for like assignment 3, looking back.
Kind of, because the way the assignments were like created. Let me see. I can just go back here. Let me see. Computer assignment 1. Everyone can do this, right? It's easy, right? You guys are masters, okay? Okay, let me just give you guys confidence boosters, okay? Because this class, I don't want it to be like a waste of time, okay? Signals and systems is great. Some people don't like the theory. It's fine. But for those who do, you can do a master's, a PhD. That's what I'm trying to do too. You can do a lot of research. Computer assignment 1, turn on MATLAB. Computer assignment 2, what do you call it? Convolution, right? Everyone can do convolution. It's computer assignment 3. Difference equations, not that bad. And he gives you some answers here too, right? Difference equations. And then computer assignment 4. This one was interesting because Dr. Stuber doesn't do this one, but Dr. Moore decided to do it. The B's and C's, is that what he called it? The birds and the bees? I don't know. B's and C's or A's and B's? I don't know. For Fourier. Anybody remember that exam? A's and B's? I don't remember. I think Stuber uses C's. You'll know why? Because complex Fourier transforms are easier. I know. Everything's easier when it's in Euler. That's what Dr. Stuber told me. Computer assignment 5, not that hard of an assignment. Really shouldn't be. You guys saw how I kicked the boxes, right? Residues and convolution. Actually, you know what? Let's do this. Generate YZ when x of n is u of n is equal to u of n, right? Does everyone know what the what do you call it? The z transform of the unit step is? Okay, actually, this is an interview question. Okay, I saw this in an interview question. They asked this, and it's basically like, do we fire this or not fire this guy? Like, can we hire him? Yes or no? X of n is equal to u of n, right? Everyone knows what that equals, right? This is n and some voltage, I don't know, and it goes like this, right? Green, it's the green marker. Wait. There we go. Boom, boom, and then boom, boom. Right? Everyone knows that function, right? Easy. And it goes to 1, right? Any questions in here? 0, 1, -1, 1 volt right there, right? Easy stuff, right? What about the Z transform? X Z, right? Anyone know what that one is?
It's just
1?
or
All right. You know what? Let's teach David, okay? The Z transform of a signal, right? X of n, right? Can be defined as this, right? Where it's equal to, what do you call it? We're going to analyze the entire signal, right? Analyze the entire signal from -infinity time to +infinity time, right? We're looking just at the whole signal, right? And then was it Z to the -n? Right? Is that correct? So if my signal is, well, the U of n, right? What do you call it? U of n, Z minus n, right? What do you call it? Right? What happens? Is that cool with everybody? And then does everyone remember about the infinite geometric series? Right? Remember that weird equation? Minus. Is that correct? No. Z to the -1. I don't like messy work. I don't like messy work. Is that correct? Everyone understand? What's the pole?
Positive Z to the positive 1.
Right? 1. That's the pole. This is where it's going to explode, right? 1 divided by 0. 1 divided by 0, right? Goes to infinity, right? Now here's the interview question. Draw the poles and zeros of the unit step. What's it going to look like? And let me just draw a unit circle. All right. Where do we draw the pole?
At 0.
Z equals
1, right? Did we do it? 0 is a 0, right? You got the job.
1. Oh, thank you.
If you didn't get this one, you failed the interview. Why is it that? Because we got to convert this to z's, right? So that means if we multiply this, let me see if it makes more sense. Hear me out. I'm gonna use another piece of paper because I like big text.
So that's what Morris said not to do. He said keep it in terms of negative or Z to the -1.
to make sure all the
Right? Then I'm going to multiply this top by z, this bottom one by z, right? Multiply by 1. That's your interview question. Okay? I'm proud of you guys, okay? But, so, no, this is correct. For when you're drawing your zeros and poles, this is correct. Because, for example, if you see something like this, hold up, 1 minus z minus 2, right? You see something like that, correct? How many poles? There's going to be at least 2, right? Because you can factor this out, right? But how many zeros are there? 2, right? Z. z squared to z squared, right? This multiplies by this to give you 1. This gives you this. That's cool, and then you can draw it like this. What's his name? It's a double pole. What do you call it? Let me see if David can remember. Because z squared minus 1, right? Okay. Do you know how to find poles? You got to make sure that you have to solve for this to equal 0, right? Is that correct? So that means z squared is equal to plus 1, right? So that means z is equal to Is that good with everybody? Any questions? So that means how do we draw the poles? So if I were to draw my unit circle again, right? Like this, right? So I have a pole here, 1, 1, right? Is that cool? And then where's my zeros? 2 zeros. Is that a cool filter? What's the frequency response going to look like? You guys want me to show you a trick? Introduce the running man. Who misses the running man? It's okay, it's a Baker joke. It's okay. Anyways, if I were to do the following for you, let me see. Let me do I want to show you that? I don't know if I should, but part of me does want to show you that. Let me just show you the unit step, okay? Right? Remember that Laplace or Z transform was this, where the pole was here and then there's a 0 right there, right? Is that cool with everybody? So I'm going to draw this unit circle right here. I'm going to start running around, okay? Okay, I'm going to run around the circle. Okay? Is that cool with everybody? This point right here should be known as DC. All right, DC, the frequency is equal to 0, right? And there's a pole right there, right? So if I were to draw my, Fourier transform frequency, right? What's the value that I'm going to get there? Well, close to 0. It's going to be high, right? Like some infinity number, right? Does that make sense? It's going to shoot up. But as I go around the circle, this 0 is actually doing something cool where, let me use another marker. Oh yeah, I love using markers. If I were right here, right? Okay. This pole still affects me, right? So it's going to pull me up, but the 0 is pulling me down, and then you're going to see something cool where it's like this. It's going to go like this, and you can draw your little points. Is that cool? But if I were, let me show you. If I were right here, right there, right? What's going to happen? Well, I have the 0 right here, right? But then I have this pole too, right? But which one's going to affect me more? The 0, right? So yeah, I'm going to be closer somewhere to 0. And then as I come around the circle, eventually I'm going to come back up to that DC, or that, what do you call it? F is equal to F sample. Does anyone know what sampling rate is? You guys know, what do you call it? Analog to digital, ADC. What's an ADC? League of Legends? Analog digital converter. And then I have, TS, right? Sampling time, which is equal to 1 over F of S, right? And I'm sampling, I don't know, some signal. If this was equal to, if F sample is equal to 1K, what's TS? 1 milli, right? Simple stuff. So that means, anyways, my maximum, you know this one. Oh, wait, you're not in 480, right? Nyquist theory, has anyone heard of the Nyquist theory? Okay, don't worry, that's a 480 thing. I don't want to talk about it. Point is, Z transforms are great for sampling, okay? You're going to notice aliasing. Who knows what anti-aliasing is? Aliasing. things that are you're supposed to not be seeing or seeing. Okay, ghosting or something like that. Basically, if you go has anyone seen like the water or not water, like a tire on the freeway? You're driving super fast, right? And you see like people's tires, and it looks like they're going forward, but there's a point where it stops and then starts going backwards, right? That's aliasing. It shouldn't be doing that because it's going so fast. It's looking like a fake image or it's ghosting. So you apply an anti-aliasing filter so you make it look like it's going forward. Okay. Same thing with video games. Okay, when you're changing your NVIDIA drivers to get rid of that aliasing, unless you want to see the aliasing. Yeah, the horse is going so fast it's going backwards. Any questions about that? So that's our Fourier transform. We can get that from the Z transform. And that's what I'm trying to show you guys right here. But you know what? Let me see. Didn't I do this the last class? Let me see. EE360 lecture. Oh man, I have different things here, right? Let me see. What did I do here? This was a Z transform. What did I do here? Z transform plotter. You know what? Let me look at something cool. Give me a second. Come on. There you go. Z transform plotter. There you go. I like this little guy. There it is. Here's my little tool. Copy paste. April 8th. Okay. And I'm going to delete all this stuff right here. Boom. Is that cool with everybody? The assignment. And then I picked this right here. Actually, I'm going to really do the assignment. Put that there. Put this here. Pi over 7. Right? And then where did I get this? Transfer function, right? The Z transform of this equation right here. Everyone can do this, right? From the last class, I don't want to waste time on this. And then if anyone's bothered, you can use this equation right here. Well, let me see, where is it? This right here, equal length functions. And it takes care of the terms here, right? Let me see. Let me go back to my thing. There's a z squared, z squared, z 1. So that means, you know what I'm going to do? Is that good? No. I think it's this way. 2r squared, r. Okay. Tell me if I'm wrong. Okay. 1 r cosine this and this. Boom, boom, boom. Are these equal? Is that good with everybody? Is everyone understanding why I'm separating like this? Ones, boom, boom, right? Everyone understanding? Okay, and then let me do my transfer function using the freaks function, freak z. Figure 1, 2, 3. Freak z of b, a, and w. Okay, what's w? W is this right here, right? W is equal to minus 2 pi times pi. We're going to do pi divided by 10, okay? 10 samples. The 2 times pi. Everyone understand what's going on? We're drawing the full circle. Okay, and let's run it. Let's see what happens. Whoa. Cool, right? Do the 100 samples. There you go. Everyone seeing what's going on? Yes, no, maybe? 0? What's this term right here? This is the DC term, right? And then boom, we have a big resonator, right? We're close to a pole, right? Think of like not like a black hole. Think the opposite of black hole, white hole. As we get closer to the pole, boom, we're gonna resonate pretty hard, right? and then we start going down, and we're being pulled down, and we don't go to 0, but boom, and then we're back there. Everyone understand what's going on? Anyways, let me see. And then this is a phase. Nothing too bad. Ooh, this is actually cute. I like this. You guys won't learn about this until maybe 480 or what do you call it? Dr. Stuberud's or Dr. Morris's 780 class, because this is very important right here. Linear phase, low distortion. Yeah, 480 is a good class. Take it. Anyways, boom, 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 boom. Is it already in dB? Okay, that's cool. Okay, yeah, I guess it does it for you. Anyone know how to use the roots function? What do you call it? What do you guys do? Help roots. Roots computes the roots of a polynomial. Let me do the following. My zeros, right? Roots of this right here. This is my numerator, right? Remember what I was doing? Okay, because I'm seeing blank stares. I don't like that. It's okay. No worries. We're trying to find our zeros, right? And our poles, we're trying to get the roots, right? Doing stuff like this, right? Everything's making sense? Let me see. Yes, no, maybe? B? Any questions? How do you make the grader happy? Of course. F print F. Is it F print F or is it print? My zeros are at D and D, or D. And then, see, because I don't think it's print. Is it display? F print F, yeah. Write data to text. And then I'm going to do my zeros. There you go. Is that cool? Actually, let me do more formal. \n, \n. Any questions? Everyone understanding what's going on there? Yes? What am I going to do for the poles? Poles. Right? I'm going to keep that there. You see what happens when you start copying, pasting things? Things don't make sense, right? But let me just do the following, okay? Just a checker, okay? If you copy paste that, you get an automatic 0. Any questions? For those who are in the class, okay? Because I already have one person copy paste the entire thing, and I'm like, I told you to copy paste with a purpose, okay? I'm really not like no BS, okay? I want to make sure you guys have fun, okay? But if I don't know. Anyways, what's the next problem? Z-plane. How do I use Z-plane? Figure Z-plane. My zeros and my poles. My zeros. Ain't that pretty? Yep. Key system, but can someone maybe figure it out? Because I'm not going to figure it out. How to make this a little more, brighter, or because on my screen it's bad. On your guys' screen it's better, but I want to make this really thick and big because I can't see it. Like my computer screen is really bad. Okay. Do you guys like this assignment? I hear the typing. Someone's doing the assignment as we speak, which is okay. Please, I encourage it. Please, I really do. Using the residues function. Was this hard? Let me see. You're boring me, Dave. It's okay. R, P, K. Residues. With residues. My B's and my A's, right? So what did I do? Capital B, capital A. And then what did he do? N is equal to 0 to 50. Okay. And then H is equal to... there's a smarter way to do this one. Who knows what's his name? Vector calculus. Or not vector calculus. Vector linear algebra. Yeah. See this right here? There's an easier way to do this. Right? Actually, before we run that, let me see this. What's R? Right here. Actually, I'll just write this right here. Come on. Gosh, I don't. We have two residues, right? Two poles, right? And then we have no gain. That's good. Okay. So what I'm gonna do is, come on. There you go. Would I make you do this? Nah. Just. We're not doing any tricks. I would love to, but we only have 8 minutes. Okay, and then figure stem, okay? NH, okay? And X label my time. Oh, what happened? Who barked at me? Right there. Error. Incorrect dimensions. Well, this is a 1 by 2, right? And this right here, okay, let me see. R is a 2 by 1, and this is a 1 by 2. Dot times n. What does this equal? Let me see. F9. The answer is 1 by 102. Great. Okay. So this is going to be 1 by 102. And this is a 2 by 1. So you know what? You guys know how to do residues and poles? Did he tell you that in class? It's page 4. You guys are going to do this for your final exam, okay? What's up?
Looking at the two ways that Stuber and Morris, they're like teaching really in different ways. It's like very, very different. Like, what's the thought process with Morris is like teaching?
Oh, everything is easy to punch in, like with a state space equation. You'll see that in the next assignment. It's pretty cool. Stuber, it's more like theory, and it's cool, and it's long and boring. I don't know. Anyways, inverse Z transforms, okay? If I had a 0 and a pole right here, right? What's the inverse Laplace, or not, inverse Z transform of this? Well, this is going to have a residue, right? And this is going to be a pole right here, right? Let's just say the pole is at 1, right? R, P, and K. Yeah, don't worry about K. All right? So here's the cheat code. Do I want to show you that? X of n is equal to R residue times pole to the n. Yeah, that's correct. Okay, is that cool with everybody? So if my residue is equal to 1, right, and my pole is equal to 1, right, then U of n. Don't forget U of n, okay? Is that cool? What's this equal to? Cool, right? So basically, if I had a bunch of poles, okay? Pole, don't forget the composite conjugate, okay? P1, P1 star, and P, I don't know, P, LOL, right? This can all be done by I is equal to 1 to I is equal to, I don't know, n of R, I, P, I, n. Is that cool with everybody? So what am I going to do? Because I'm too frustrated to like even solve this. Going to do it the hardcore Stubbery way. That's what I was taught. So what am I going to do? R1, right? Dot times P1, right? Dot times N, right? Right? Plus R2 dot times P2 dot to power N. Any questions? You guys going to do this on the exam? Booyah, baby, let's go. Kicked in the box. Cool. Who wants to see a unit step? Actually, no, I don't want to do a unit step, okay? We got 3 minutes. Maybe I will do a unit step. Maybe I will. B's, A's. This is a transfer function, right? Transfer function, right? Yes, 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 yes. Transfer function of a unit step. B, U. What was it? Right? A unit step. Everyone understand what I'm doing? We gotta punch this in MATLAB, right? I'm gonna use the yellow marker, right? MATLAB, right? We got a position, we have a Z right here, and a constant one right there, right? So it's gonna be 1, 0, right? Can everyone see that? Pink marker. We got a 1, minus 1. Everyone understanding what's going on? Okay? Woohoo! So what am I going to do here? I don't know. B answer is equal to B. No, wait. Where is that? Where's that funny convolution? Do we have to use convolution? The con function, right? Con B, U, right? A answer. A unit. You know what? I'm going to leave those uncommented. What's B answer? 1 by 4. What's A answer? Also 1 by 4. I'm not going to show you guys the numbers because I don't want to. Because who needs the numbers? Because we have MATLAB. Okay? So, run this thing again. Right? We're going to kick that box. Boom. Residues. B answer. A answer, right? RPK, I'm going to do, you know what? I'm lazy. Boom, 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 boom. Boom, boom, boom. You guys like this? Cute. And then what was that thing that Papa Dave told you? R answer 1. Actually, you know what? Before we even do that, let's calculate. Okay? Where's my R answer? Our answer is 3 by 1. Okay, let me just double click on that. 3 by 1, right? That means we have 3 residues. What does that mean for our poles? 3 poles, right? What about K? K answer. Hopefully it's a good day. 0. Woohoo! I don't want to teach you guys the K's, okay? So H answer. This is where linear algebra, if you took in Math 330, helps, because I can't figure. Look at this. I have to type this 1 dot times P answer. So if you want to do this for homework, please, you can. Try to find a way to make this shorter for me, because look, I'm about to type a mess. Okay, plus dot 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 plus. Is that the right? Is that right?
Just like, like a for loop pretty much?
No, not a for loop. Don't do a for loop. For loops are painful. There you go. 2 and 2. Okay? Let me just run this up here. Let me put some space right here. Cool? What am I going to do? Copy paste. N and wait a second. Did I use the residue function? B answer. Wait, did I? Where did I use N? N 0 to 50. Oh, okay. Sorry, I'm blanking out, everybody. H answer. Woo! And when you kick the box, right? It's a unit step, right? So it's gonna set to Vn is equal to 1, right? RC filter, right? It's gonna settle to 1 volt, right? Is that settling to 1 volt? Step function. It's on your midterm too. Any questions? Have a good day.